Hello, it's Keith here, and this is lesson 4 of the SuckShoot series of my ARM assembly programming tutorials. In the SuckShoot series, we create the game SuckShoot, and today we're looking at the RiscOS version. I've ported it from the Game Boy Advance and Nintendo DS to RiscOS, and you can see the game just here. So the game is basically the same as before. We move our cursor and we shoot bats, and we potentially have a lot of fun. But actually probably we won't, because it's a very simple little game. Now, one limitation of the RiscOS version is that I don't have a Chibi sound driver. Chibi sound is my simple sound effect driver that I use in all of my games, and I haven't got one for RiscOS. So while the sound driver code is still included, the calls to the Chibi sound routine are still included, the Chibi sound routine is just a generic return. So there's no sound at this stage, but if I write a Chibi sound driver later in the future, this game will immediately support it, because as I say, the sound code is still in there. Anyway, let's go over to the source code and let's actually take a look at the RiscOS version of this game. Now, we're not going to cover the generic code that hasn't changed. Please see the first episode in the SuckShoot series for that. We'll cover things, the main loop and the details of how the randomization works and things like that. Today, we're just going to look at the RiscOS code. Now, at the start of our program here, we have a RAM area, and the RAM area is used for exciting things like the stack, but it's also used for our game variables. So we're defining some bytes for the score, which is a 4-byte binary coded decimal value, the high score, the sound timeout, the lives, the random seed, and 8 bytes for the enemy data, and these are for the coordinates and the other settings of the enemy, and these are defined as offsets from the base of the enemy data here. We also need a cursor X and a cursor Y. These are for our character drawing routines, because we're using a bitmap font of our own design in here. So that's how we're doing things. We need some memory for those. Now, at the start of the actual program, we're setting up the stack, and then we're setting up the screen. Now, we are using the 16 color mode. We're using a 320 by 256 pixel screen mode for this, and there is a problem that causes us, because our game code is designed to work in single byte X and Y coordinates. Well, a 256 Y coordinate is fine, but a 320 X coordinate isn't going to work so well. So we're actually working in pairs of pixels across the screen. So our screen in logical units is going to be 0 to 160, and we'll double that up if we ever need to work in pixels. So that is how we're doing things. So we are setting up our screen here with SWI36 in hex, but then we are getting the parameters, which are basically the screen base, the memory address of the VRAM base, using 31 here, SWI31 hex. So we're doing that. We're then setting up the palette with our set palette routine. Now, if we just have a look at that quickly, that is also using an SWI to set up the palette. Now, the palette format in the data here is in this format here, 1 nibble per color channel here. And then what we're doing here is we are basically taking that and we're masking it out, and we're sending it to the screen using SWI0. We have to send special character codes to the screen here to do that, and then we send the red, green and blue components to set up the screen. So that's how we're doing things. Now, the sprite data itself is I made, as always, with my Acro Sprite editor. We've got the sprite for the player, the 3 different scales and 2 pairs of bat animation sprites here, and we exported these with the ARM option RiscOS, and we saved 16 color bitmaps here. We're using the 16 color mode because the game doesn't really justify even 16 colors really, if I'm honest. So we're just defining that there. And we've got the sprite info table here, which I've covered in episode 1 of this series. It's basically a lookup that gives the offset within the sprite bitmap data of each of the numbered sprites and the size of the sprite accordingly in pixels. So we're going to need to convert that later on. Okay, first of all, let's have a look at our CLS routine, because that's the easiest thing that we do with regards to the screen. Now, our screen base is a variable in memory which has been set up during the initialization with the base memory address of the screen in VRAM. So we're loading in from that pointer there, and that will be the VRAM base that we need to fill. Now, we need to fill 320 by 256 pixels, and there are 2 pixels per byte, and we're able to transfer 4 bytes in one command because we're working in 32-bit words here. So we are dividing the number of pixels by 8 to get the number of words, and then we're just repeatedly writing zeros to that range there, and that will effectively clear our screen. Now, if we have a look at the print char routine, where is it? There it is. So this is our print character routine. Now the way this will work is we will calculate from a cursor X and a cursor Y position, which is a character position, and we will calculate the base, and then we will transfer our font to the screen. Now our font is in 1 bit per pixel format, but our screen is in 4 bits per pixel format. So we will need to convert it. So first of all, what we're doing here is we're loading the cursor X and the cursor Y. We're loading those in, and then we're loading the address of our screen base. And what we're going to need to do is we're going to need to calculate the offset in that screen base based on that X and Y coordinate. Now, each of our characters is 8 pixels wide. There's 2 pixels per byte. So we multiply the X position by 4 to get the byte position across the screen for the character we want to change. Now, that's our X position. Our Y position, well, our screen is 320 pixels wide, but there's 2 pixels per byte, so that's 160 bytes wide, and there's 8 lines for each of our character blocks. So we multiply the Y position by 160 by 8 to get the offset, and we add those two together, and that is the offset within our screen base that we need to print this character to transfer the bitmap data to the screen to draw the character. We calculate the offset in our bitmap font of the character we want to show. Our font has no characters below 32, so we subtract 32. There are 8 lines, and each line is a single byte. So we shift the character number by 3 bits to the left, effectively multiply it by 8 to get the offset for the character we want to show. We then need to transfer 8 lines from our source bitmap to the screen, and the way we're doing that is basically we are getting a single byte from our source, and then we are transferring the bits of that, and we're shifting them into the correct positions in the destination here of our font here. So we're effectively shifting all of the bits into a 32-bit word, that's 4 bytes, which is 1 line of our character across the screen. So we've got all of the 8 source bits into that 4-byte destination here. We're just shifting those in, and then what we're doing here is we're basically multiplying that up, and this is effectively setting the pixels to color 15 within our palette. That's what I tend to do in these tutorials, use color 15, and we're then storing that to the screen, moving down a single line, because all of this has basically done a full line, 4 bytes, remember 8 pixels, so that's done an entire line. We then repeat for the remaining lines of our font, and we then move across 1 line, moving our X position across the screen for the next character we show. So that's how our print character routine works. Now you'll see that basic kind of function again within our show sprite routine. Now our show sprite routine uses the sprite info table, which is that table of offsets within the sprite and X and Y width and heights, and it will be used by this routine. Now the routine itself is passed an X and Y coordinate for the sprite. The X coordinate will be half the pixel coordinate, because as I say, it's a single byte. The Y position will be in a number of lines, and what we actually need to do is we need to center the sprite. So we're past the center position, but then we need to move to the top left corner so that we can draw our sprite to the screen. The reason we pass the center position is because we need that for our range checking routine. So what we're doing here is we are adding the offset to the sprite info table. Now at the start here, we are converting the X coordinate from logical units to actual pixels here, and then at this point we're loading in the width in pixels, and we're halving that, effectively calculating half the width and subtracting that from the X coordinate, and that effectively handles the centering of our sprite. We're then doing the same for the height, loading in the height, halving it and subtracting that from the Y position. This means that we've gone from a center position to the top left of our sprite, and then we will continue to fill that to the screen. Okay, so we've got our X and Y coordinate now. We're then getting the screen base, again that's the VRAM base of our screen. We are multiplying the Y position by 160, that is calculating the Y offset. We are then adding the X position here in bytes, and that is now calculating the destination. What we're doing here is we're loading the address of the sprite bitmap data. R11 here is still pointing to our sprite info table. So as we got the width and the height here, this time we're actually getting the memory address of our sprites here. So this is now in R1 our source bitmap data address. So what we're going to do here is we're going to transfer the entire sprite to the screen. So what we're doing here is we're loading the width and height in pixels here into these registers here, and then we are transferring a byte from our source XORing it to the screen, or EORing it rather, so that this is being written back to the screen. And the reason we're using EOR or XOR is this is an inversion trick, and this basically means we can draw the sprite to the same position twice. The second time we'll remove it, which makes it a lot easier for our graphics routines. Just a simple way of doing things. Now, with each byte that we transferred to the screen, we transferred 2 pixels, so we're subtracting 2 from our width here, and we're then moving here, and we're going to move down a line, and each of our lines is 320 pixels, 160 bytes, so we're adding 160 to our VRAM destination, and we're subtracting 1 line from our line count, and we're repeating until all the lines have been drawn to the screen. And that's basically how we're drawing our sprite to the screen. It's not too difficult really. So that's our sprite drawing. Now the final part of the equation is the joystick routine, which is a total lie. It's a keyboard routine. We're cheating. I've called it read joystick because I'm trying to give everything the same names on all the systems so that I can more easily port my code. So read joystick is actually read keyboard, and we've got a function here called key test1. Now our build up byte is going to start at 255, and we'll set bits of that to 0 depending on if the key is pressed down, and the order will be from bit 0 up, down, left, right, fire 1 and then fire 2. And we're going to use keys for each of these, and so we're setting the R10 register to the bit that we want to set to 0 if the key is pressed, and we're setting R1 to 255 XORed with the key number. And the key numbers, you will need to check the RiscOS documentation. If you look at my website on the RiscOS page, I have the key numbers shown there, and so we're setting the correct key numbers here according to the key we want to test. So first we're testing up, which is key 57, so we move R1 with 255 XORed with 57 here, and that is the test that we want to do, and we want to set bit 0 if that key is pressed, and we're running key test 1, and we're going to do that for all of the other keys we want to do. Up, down, left and right on the cursors, space is our fire 1 and enter is our fire 2. And the testing routine is pretty straightforward. We need to load R0 with 129, R2 with 255. Those are fixed values for SWI6, which is our key test routine. And if this returns a 255, the key is pressed. And so if the key is pressed, we're going to AND the mask that we passed in with our build up R9. And R9 we will build up with all of the key presses, and then at the very end we'll transfer it to R0, which is what we want for compatibility with the code that was transferred. This was ported from the Game Boy Advance version, so we're maintaining compatibility there, and we want that build up value in R0 there. So that's how we're handling the joystick reading, and then you can see my rather sad chibi sound routine here, which doesn't have any sound. I don't have a sound driver for RiscOS yet. Anyway, there we go. So that's the basics of this code. Now, obviously, there's a lot more bits with regards to the range testing, the random routines, and so on. If you want to see more of that, please see the multi-platform series where I covered how the random routines and range checking work, and the binary coded decimal, and also the first episode of this series where I go into more detail of how the sprites work in general terms. I looked at the Game Boy Advance version, but the code hasn't really changed, so please take a look at that if you need to see more. Anyway, that's all we're covering today here. Now, if you liked what you saw today, please consider backing me on Patreon, because to be honest, I don't think I have any Patreon backers who are interested in RiscOS, and as I've never owned a RiscOS machine and never wanted to own a RiscOS machine really, it shouldn't come as too much of a surprise that I haven't spent my weekend learning how to write a sound routine for RiscOS yet. So if you want to see better tutorials, please consider doing that. Anyway, as I always say, go to my website, download the source code and the build script and all that stuff. You're welcome to use the source code in any way you can. If you manage to make SuckShoot4 and make $100 billion in the process, good luck to you. I'm sure you deserve it. Just buy a copy of my book maybe. Anyway, thanks for watching and goodbye.